All right. There was a request for a key to this thing, so let's chat about it here. We've got a system schema, free body diagram for a box that slides at a constant speed across a frictionless floor.
Attention students, there will be a music play-a-thon in the West High cafeteria this Friday evening. The event will take place from 6 to 9 p.m. and have feature performances from West High students. Tickets will be on sale today, Thursday, and Friday during lunch in the Commons. Tickets are $5 for students and staff and $10 for adults. They will also be sold at the door. All proceeds go to the music auxiliary.
All right, so I hope you got all that. So I'm just slapping out a system schema here really quick. So there's a box, clearly, talks about a box, talks about a floor. The box is touching the floor, so there's smoosh poosh. Box is near the earth, probably, so I'm going to think some G there. So right now, this is looking like my free body diagram has two arrows. I should also mention here I underlined constant speed. That wording means that this is CVPM, and if it's CVPM, then I know that the forces need to balance. So I'm going to draw gravity on the box. Should label that the dot is the box. So this is FG box, comma Earth. And this upward arrow is FSP box, comma floor. And I didn't draw the surface in here, but had I, you'd see that that smoosh pushes 90 degrees to the surface. It doesn't say anything about a baddie, but if I did, I'd have arrow up followed by arrow down, and it'd go right back to where it started. These are the same length. Forces balance, CVPM. All right. Next, system schema, free body diagram for a box being pushed by a student but not moving. Okay, not moving means that the velocity is 0 and it's constant, CVPM. So therefore, it should be BF PM. Label the forces with the feeler dealer and use equality marks on force arrows where appropriate. So system schema, I've got the box, I've got the student. Looks like there's a wall here. I've got some kind of a floor. I've got the earth. Box is touching the wall, so there's some smoosh poosh there. Box is touching the student, smoosh poosh there. Box is touching the floor, smoosh poosh there. Box is near the earth, gravity there. Yeah, I can connect these things up. What's your great grandmother's name? The thing that we're interested in is the box. So free body diagram for the box. Box. I've got gravity, straight down, FG, box, comma, earth. I've got a smoosh poosh up from the floor, so box, comma, floor. And again, if I think about my surface, that arrow is 90 degrees to where the box touches the floor. And then I've got the smoosh push from the wall. Smoosh push points away from the dealer. So again, this upward arrow is pointing away from the floor. So the one that points this way is pointing away from the wall. That's FSP box, comma, wall. And if you think about the wall, then this arrow, well, I guess I already have this here. This arrow is 90 degrees to that surface of the wall. And then there's an arrow going this way, and that's got to be FSP box, comma, student. Okay, because again, it's pointing away from the student, and that would be 90 degrees to where the student is contacting the box over here. So if I do another 90 degrees there, you get the idea. If I baddie these arrows, arrow up, arrow right, arrow down, arrow left, that path should lead back to the beginning. They're not necessarily all the same length, but the left and right ones have to be the same, and the up and down ones have to be the same. All right, last one, system schema, free body diagram for this box attached to a rope. It said rope, that means something. It's falling at a constant velocity. So here's the box. Ooh, let's do a system schema quick. We got box, we got rope, we got earth. There is a pulley there. I could include that if I wanted. The rope's interacting with the pulley. Okay, so box rope, it's a rope, it's probably tension. Box earth, so that's gravity. People bugging me, they can go away. Let's see. All right. So for the box, it looks like there's two arrows. There's F, G. That's going to point down because always box, comma, earth. And then tension points in the direction of the rope. The rope's above this thing, so it's going to pull up. FT, box, comma, rope. And this thing is moving at a constant velocity. CVPM means that the forces should balance. So those arrows are the same length. But Mr. Harding, I can't tell it's falling. Yeah, well, look at a position versus time graph, velocity versus time graph, or motion map if you want to know that, my friend. The baddie tells us that the force is balanced, so it would be CVPM. Moving along, so there's this problem. It's kind of like the force table. So when you're dealing with this type of thing, 20, 90, 180, so on and so forth, that's kind of like relative to the compass direction. So I'm going to lay my compass on here. I'm going to always keep 0 degrees up, okay? And so if you think about where, I'm going to probably start this in the middle, and here's 0 degrees. So I'm going to measure over 20 degrees, and I'm going to have my 3 Newton arrow, and then I've got 4 newtons at 90 degrees. If 0 is up, you can see 90 is over to the right. And then I've got 5 newtons at, circle it here, 180. 180 is opposite of up. So that's going to point like this. And then I'm looking for what is the force and angle here. So I just connect the end of my 3rd arrow to the beginning of my 1st arrow, because this is the 4th arrow that balances it all out. And I did that over here on the paper, and you can see what this looks like. Okay. Now you could do this in any order. You could have drawn the 4 newtons, and then drawn the 3 newtons, and then the 5 newtons, and you should still end up with this same answer of 5 newtons at an angle of 294 degrees. Or maybe you draw the 5 first, then the 4, then the 3. That should still result in an arrow that's pointing the same way, right? That's the summative property of addition. Doesn't matter what order I add them up in, it should still yield the same answer there. Okay, so that's what's going on with that one. 5 newtons at 294 degrees. And then scrolly. Determine the mass of the unknown object in kilograms. It says it right there. If it's mass, it wants kilograms. If it's gravity or weight or force or whatever, it wants newtons. Okay, but it says mass. Assume it's motionless. Velocity is 0, therefore CVPM, therefore BFPM. The only force I'm given is this is 5 newtons, but I know this angle is 20 degrees. I have to be smart and recognize that it's 20 degrees to the vertical, and that this is 50 degrees over here, again, with respect to the vertical. I don't know this amount of force. I'm calling this RC because it attaches to the ceiling. I'm just calling this R1. And then clearly there's some gravity here. All right, so I'm down to my diagram. The first thing I drew was, I started out, I was going to draw it here, and then I thought about it. I'm like, wait, we're only going up from here. So I got out my ruler and my protractor, and I measured over 20 degrees. Okay, and you can see that mark right there that I made with my protractor. And then I drew this 5 centimeters long, because 5 newtons. Okay. And then what I did was a couple of things. So on the end of it, I made an H, and I made a V, vertical reference. And I remembered that this angle here is 50 degrees V. So when I'm down here, I want to measure that 50 right here. Okay. Sometimes in the past, people would put that inside the triangle, but it's with respect to the vertical. I didn't know how long this was yet. Okay, I just made this mark over here, and I kind of made a bit of a long line pointing in that direction. Here's the key, is gravity is going to have to be straight up and down. So I also had this in here. I had a reference line that was straight up and down like this. Okay, and basically I'm just trying to figure out how far over do I need to draw this So it's going to be straight down to get back to the beginning. Okay? And so that is what allowed me to figure out that from here to here, 2.2 centimeters, so that's 2.2 newtons. Okay? And then from the end of that arrow down to the beginning, 6.1 centimeters, that's 6.1 newtons. Now I'm not done. It wants the mass in kilograms. 6.1 newtons, and there are 10 newtons per kilogram. So I'm going to divide by 10 newtons per kilogram, and units-wise, that would push the kilograms up top. And so this is going to be 6.1 divided by 10, so 0.61 kilograms. Ta-da. All right, good luck to you.